Welcome to the tinyML Asia 2020. I'm Hye-jun Ryu. I'm a professor of electrical engineering at KAIST Korea and chair of today's session, the plenary session and session number 1, hardware session. And it is my pleasure to be on the technical program committee for the tinyML Asia. Okay. It is my great pleasure to introduce Professor Lee from Institute of Electronics, Tung University at Hsinchu. His presentation is toward the data-driven applications with AIoT devices. Professor Lee received his PhD degree in electrical engineering from Catholic University Leuven, Belgium in 1990. He is currently a professor in the Institute of Electronics, National Tung University, Taiwan. His research interests mainly include various algorithms and architectures for high-throughput DSP and data-driven applications. He's also active in various aspects of microsensing, low-power system on a chip, and machine learning. He holds more than 50 US patents and co-founded 4 startups related to data-driven applications. Professor Lee, please.
Yeah, thank you, Professor Jung, for the introduction. Today, my presentation topic is related to data-driven application with AIoT devices. And the title, in fact, is based on my past 8 years experience working on this topic from academia to industry and then back to the academia again. So here is the outline of my talk. First, I will talk about the application scenario and try to use some example with AIoT device to demonstrate the opportunity and the challenge remain to be solved. Then I will talk about 2 major technical issues. One is related to resource-constrained AI model generation, which is the current solution for inference. And the other is how to improve the accuracy by including the meta-learner in the AIoT devices. Finally, is a summary and some future direction for future work. So, as I just mentioned, if AI solution to be accepted, we need to consider the opportunity. And in principle, the application can be classified into 2 categories. One is AI solution for current industry. For example, like in manufacturing, we can include an AI solution to improve the yield and the process control. And even for certain area like business intelligence, we can improve the service quality and also the case control. And the other cases like smart home or smart city, with the AI solution, we can improve the quality of life. However, if the solution is to be used in current ecosystem or infrastructure, normally the end customer, they think that the AI solution nice to have, but not always must have the AI solutions. That means the solution are defined or dominated by the current industry or the key player, and also the profits are defined by the key player too. And it's hard for the AI solution provider to find a good business opportunity. For this current industry, normally, we will face the problem like the limited data sets and the accuracy, and also they need to have the cost down, and in addition, the power consumption as well. And for the second category, that is, we try to enable a new business opportunity by taking into account the new AI solution. That means that we can create a new business opportunity in several emerging market segments. This indeed happened during or after the COVID-19. There are so many new business opportunities which are not addressed for the moment. And here, the business model are very different from those available as we see now in the market. And these new market segments are mainly created by young generation who used to enjoy the internet services. However, to penetrate this new business of this new market, we need to conduct proof of concept service and the business, and besides, we need to educate the market. And in that case, we need to consider data availability, security, and even the accuracy to reach a certain level of service quality. And of course, the business and the capital investment should be considered as well. In summary, that for this new business track, several major issues has to be overcome, like limited data set, accuracy versus cost, and also the profit model as well. So in order to let you understand the new business issue, we highlight 3 examples which has been deployed in real environment in Taiwan. The first one is the automatic gauge reader, or called AGR. The original design is for data recording in small to medium-sized manufacture and with this, the data can be collected for analysis to reach better yield and process control. However, this solution can be applied to smart city or smart home to save electricity and water. And very often, these devices can be realized by camera and with some embedded system as shown below. And for the second case, that's wearable ECG devices. The original design is mainly for mobile health care. It collects data set and then do the analysis. However, the motion artifact has to be removed in order to maintain the accuracy. And recently, we have applied this solution to fitness and sport service to enhance the quality, so that the real-time stamina monitoring can be achieved. And because of this new application, the phone size and the power consumption is the major issue, so that's fine. And ASIC has to be designed and to reduce the noise and also to save the power. The device and the chip are shown below. And for the second example is the camera devices for entry control and the video surveillance. So you can see that from this, the solution is to cover face detection and face recognition on the different background lighting. So the pre-processing is very important. And in addition, you need to consider the wide face angle during the recognition phase. And if the solution is to be deployed for general surveillance or entry control, you need to consider the multi-camera in one powerful server. However, if the solution to be deployed in drone, then you need to consider power and also the font size as well. So from these three typical examples, very often the guideline can be derived, such as model training to collect valid data set with labeling, and then use available model or create a new model to reach acceptable accuracy. And for hardware design, we need to consider the volume issue. So you need to define the specification to do model reduction, and also how the model can be realized in different hardware platform like ASIC, FPGA, or embedded system. And the other is you need a lot of field trial in order to ensure the robustness in real environment. And of course, the solution has to pass the data security regulation in different areas, and try to have some successful story for market promotion. So for the first technical issue, we talk about the resource constraint network architecture search. Very often, we select a deep neural network of DNA model and try to do the model reduction. But how can we select the numbers of field of neuron in a deep network? Is it small or large, or how the job can be done with the minimal engineering effort? And from the observation on the current network pruning solution, it's shown below. It's from training to pruning, and then do the fine tuning. These three stages, and it can be found that the pruning can be viewed as an architecture search method, and there should exist a sub-network that learn faster than the original network and can reach better high test accuracy. And of course, the relation among the hyperparameter can be further exploited. So based on this observation, in our lab, we recently developed a new solution called the neuron scale. It's mainly for resource constraint architecture search, which has been published in this year, CVPR. The hypothesis is given a deep neural network of DNA with minimal redundant parameters through the modeling of the change of neuron in each layer, and with respect to the network structure in the total parameter of the DNA, we are able to scale the network architecture in various sizes and in a very efficient way. So the formulation can be divided into three stages. The first thing is to perform iterative pruning, and then the parameter pruning progress. And then the last one is scale the network accordingly. So these slides just show the difference between our proposal and the conventional approach. The left part is the current solution based on uniform scaling. So that means our layer we scaled with the same parameter. But in our proposal as shown in the left figure, you can find that we try to do the architecture descent, try to parameterize the process at different each layer. So each layer structure with the field size all the way, the parameter can be tuned based on the input data features. So we coded it as a neuron scale. So with this, you can see that the accuracy for the left figure, if the model size is fixed, then our proposal can reach much higher accuracy. And on the other hand, if the accuracy is fixed, then our model can achieve much less model size. This data are derived from the mobile net version 2. So with through the parameterization of the printing progress, it is able to scale any neural network with the neural structure or filter, in a very efficient way. So with our formulation, we can also apply to reduce the hardware complexity. We call it layer-wise quantization. So that means the word length allocation and also the optimal clipping for weights and the combination can be optimized by considering the noise importance. So as shown in this figure and the table, it implies that with our proposal, combined with layer-wise bit allocation and also the optimal clipping, the results show that different model, our proposal can reach almost the same accuracy as those obtained from the 32-bit floating point. So this is the first part, related to the optimization of the hardware architecture. And the second part is for the meta-learning. The reason why I talk about the meta-learning is because when the device is deployed in real environment, we will face several issues. The first one is the problem of deploying deep neural network to the real world. And normally, the input may have a lot of dynamic change in the distribution. And how certain are we that the training distribution cover all possible application scenario? And this is very important because the accuracy may drop a lot. And the third one is when the devices are deployed, the new level data are not easily attainable. So that means it's not easy to modify the model. So very often we are using the static model that is the inductive inference, like the traditional supervised learning, and the model is trained using the labeled example. However, the model is fixed and cannot be fine-tuned. And we propose the transductive inference. We include the initial model, which is learned using the label example, but we try to reason from the training cases so that the model can be adapted to the input statistics during the test phase. So based on this concept, our network architecture can be divided into stages. The first two are just like the traditional one. It contains a convolutional encoder mainly for feature extraction. And then with the targeted estimator, the result can be predicted. However, we also include the synthetic gradient generator and try to fine-tune the feature extraction part, which can be adapted to the input statistics. Then the concept is as shown below. So the right figure shows that if the data belong to the input distribution, that means that during the test phase, the accuracy can be maintained. However, if the input is in the region of out of distribution, then the result becomes very worse. So that's why we propose the prototypical distance minimization. So that means during the test phase, the input dynamic or distribution or statistics can be fine-tuned to approach the center. That is the plot shown here. So the formulation can be shown below. We formulate the proto of the data and the variable is a specific task, and then during the training phase with the label data, we can obtain the global data and the variable prototype as shown in the equation. So I will try to use the meta RPBG, which is used for phase heart rate as the application to demonstrate the feasibility of our proposal. So you can see from here that's the normal testing procedure. Then you can get the heart rate from the extracted RPBG signal, but we also include the proto and the synthetic gradient generator. So that means with these two modules, the input statistics can be updated during the testing phases, and in that case, the accuracy can be improved a lot. And this slide is just demonstrate the performance of proposal now using the public domain UBFC RPBG databases. You can see from this table, compared with the baseline or the inductive, our proposal can reach much higher accuracy with proto, synthetic only, or even combined with both two. And so that means using a meta learning network, state of the result can be achieved in the AIoT devices. And this slides just demonstrate the capability of our proposal. The left is the original phase, detected from the video, and the middle part, is the heat maps, and the right part is the extracted heart rate, and you can compare that the predicted result is very close, to the ground truth, and of course, in real application, you can add the specific constraint to the devices so that the result or the prediction will be more accurate to meet real life application. And with this, I would like to summarize my presentation. I use some example, to demonstrate the AIoT devices for real life applications, and point out to a technical issue, how to reduce the complexity in DNA model by the so-called resource constraints and neural architecture search method, and then introduce the Transductive Inference approach in AIoT device to further enhance the accuracy during the deployment. And the future direction is addressed by the presenter in the previous talk. We may enhance the inference accuracy with the energy efficiency neural network model, both in algorithm and the hardware. And we may also explore the new computing architecture, like the in-memory computing is presented in the early speak. And also, we may consider the chiplet solution for faster prototyping with the available bare dies. This is very important because from my past experience, the AIoT devices sometimes it's not with a high volume, and we need to create a successful story based on available hardware resources. So I would like to acknowledge the financial support from most and MOE of Taiwan, and also my students, in SI2 research lab, and the cooperation partner from UC Berkeley and the Stanford University. And this is the last slide. For those who are interested in our work, you can find the source code related to scale and the meta PPG from these slides. Yeah. Thank you for your attention. Thank you.
Thank you very much for the nice talk about the AIoT design. And there are some questions. The simple one is for the automatic gauge readers. How long are their expected battery lifetime? Yeah,
I think it's a very good question, because when we deploy the solution to the manufacturer, the solution in fact is based on Raspberry Pi and combined with I think it's the Wi-Fi connectivity. So the solution can be run for a few weeks, and if it's connected to the power, then the solution can be run for a long time, and the server just collect your data and do the following analysis. But if the devices is operated by battery, then the solution can run for 1 day, and the next day they can replace the battery. Yeah, something like that. Yeah.
I see. Okay. Another question is the target microcontroller, about the target microcontroller for actual testing. Is ESP32 is an acceptable target or not?
Pardon me? Okay.
Oh, those you need have a target microcontroller for the actual testing, right? And is ESP32 an acceptable target microcontroller?
Oh, yeah. I think that's our target, because that's the benchmark. Try to see if our solution can reach high accuracy, and that can be accepted by the end customer. So from our past experience, if the solution is high accuracy is high enough, then the next issue is they will consider the price. So you need to pay attention, to how the model size, can be reduced to a certain level, so that the end customer, can accept it.
Yeah, and another question is the energy efficiency is very important. But the performance of the neural network itself is also a very important figure of merit. So what kind of performance of the IoT network should we consider as the whole? I mean, the balance between the energy efficiency and the performance.
Yeah, this is a very good question, also very important. I would say that it's very application dependent. For example, like 3 examples I just addressed. For the energy efficient solution is very important for wearable devices, and for this application, normally the data rate is not so huge, so you can enhance the accuracy, but in the meantime you can limit the power consumption under a certain level. As the devices I show that the power consumption is below 1 milliwatt. But for entry control or for the AGR, then the solution normally you can consider maybe it's run for 1 day or 2 days or 1 week, etc. So that really depends on the application scenario.
Yeah, and also in your slide, you mentioned the robustness. Robustness is very important. How big is this issue? And is it so serious preventing people from deploying AI to many devices?
Oh yeah, that's the real problem. In fact, many IC provider, they face the same issue because when their IC is deployed, the end customer may ask that they need to change the model to allow more clarification model or to allow more object types. So the robustness means that you need to consider the deployed environment, also the variation of the devices to the environment. So with our proposed meta learner, and we recently applied this method to real application, and we found that the average about 4 or 5% can be improved, and this improvement can be accepted by the end customer, and they can accept the solution. Yeah.
Yeah, thank you very much for the nice Q&A session. And also thank you for your nice presentation. We would like to thank our sponsor again, who have made this event possible. Our premier sponsor, ARM, the software and hardware foundation for tinyML. And Edge Cortex, with the dynamic neural accelerator architecture and co-exploration engine, brings cloud-level performance to the edge. And Sixth Sense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. And thank our partner organizations, Chiao as our conference partner, and all of our media partners. And you have found them all listed on our website, tinyml.org. Thank you for joining tinyML Asia 2020 with us today. We look forward to seeing you tomorrow.